Welcome back to Chapter 2. We're on Lesson 4 on real zeros of polynomial functions. In our last lesson, we learned how to factor polynomials and sketch the graphs based on leading coefficients and the power of the polynomial. And in this lesson, we're going to focus on finding the real zeros of the polynomial functions. And I want to emphasize the word real zeros. We're not going to have any complex numbers, no square roots of -1. We're going to focus only on the real zeros here. And we're going to learn a new method of division called synthetic division, and I hope you're familiar with that from Algebra 2, but if not, it's a pretty simple thing to learn. So let's go ahead and start out with an example. This example says divide using long division. And so we have 2x to the fourth minus 3x cubed plus 5x minus 1, all divided by x minus 2. So the number on the bottom goes outside, and the whole polynomial that we are dividing goes on the inside of the division bar. And then we look at what do we have to multiply x by to get 2x to the fourth. Well, we have to multiply that by 2x to the third. So when we multiply the entire thing on the left by 2x to the third, when we distribute that, we get 2x to the fourth minus 4x cubed. Remember, we're multiplying both terms by 2x to the third. And then I always put parentheses around that and put a subtraction sign in front of it so that I remember that I'm subtracting from the term above it. 2x to the fourth minus 2x to the fourth is 0x to the fourths. And then we have minus 3x cubed minus a minus 4x cubed. So this really becomes a plus 4x cubed, which gives us 1x cubed. And then the next thing I wanted to make sure to point out, notice that we're missing an x squared term here. So you always have to put a placeholder when you're dividing if you're missing a term, and they have to be in descending order, your polynomials do. So I just bring down that x squared term even though it's a 0. And then ask yourself, what does x need to be multiplied to make it be x cubed? Well, it has to be multiplied by a positive x squared. And then multiply the x squared by the whole thing on the left-hand side. And then it's going to be subtracted. I didn't put my subtraction sign there. I think I just need to delete that one. There it is. And so when we subtract those, the x cubed terms are gone, but we get a positive 2x squared. And then to get x to be 2x squared, we multiply by a positive 2x. Bring that down after we multiply the outside term, we get 2x squared minus 4x, and then we're subtracting. So we end up with 9x, bring down your minus 1, multiply by plus 9, and subtract that, and we end up with a remainder of 17. This remainder then we would write like this. We would say this is plus 17 over whatever we were dividing by, which was x minus 2. Don't write remainder 17, add it as a fraction in the end. So that's kind of a long process. As long as we have a term that looks like this, either x minus a number or x plus a number, we can use what's called synthetic division. And this is a pretty neat process, pretty slick. And what you do is you end up just writing your coefficients. And again, you need your placeholder for that squared term. This is the exact same problem, and we should end up with the exact same number in the end. So to start the process, x minus 2, if you were to set that equal to 0, we would get x minus 2 equals 0, or x is equal to 2. So the number that goes out on the shelf here is the way I like to phrase that, is what x is actually equal to. So that's a 2, and then you start by bringing down the first number. And then you multiply diagonally. What is 2 times 2? Well, that's 4. And then we add these terms. 2 times 2 is 4, so we're going to get, I think I didn't do this one, so that's a 4. And then we add. 4 plus a negative 3 is 1. And then we multiply again. 2 times 1 is 2. Add 2 and 0, you get 2. 2 times 2 is 4. 5 plus 4 is 9. 2 times 9 is 18. And 18 minus 1 is 17. So you'll notice we get the same remainder. So what that says is this. When we're dividing these, remember we just dropped all of our variable terms. So what we end up with is x minus 2 multiplied by, now we can go ahead and add these variables back in, and these will be one less than what they started with. So we started with an x to the fourth term, so this will really be 2x cubed plus x squared plus 2x, and they just go in descending order, plus 9, and then it's plus 17 over x minus 2. And that is how that would factor. So another way to find a remainder, if we were looking just to find the remainder, is to actually evaluate the function at that value. So this is the same equation that we've just divided using long division and synthetic division. If we were to actually evaluate that at x equals 2, we just want to plug in 2 for the variable x everywhere x occurs. So 2 to the fourth power is 16, and 16 times 2 is 32. 32 minus 2 to the third is 8, and 8 times 3 is 24, and then plus 10 minus 1. Well, this gives us 8 plus 10 is 18 minus 1 is 17. So we end up with that same remainder no matter which process we use. So why do we care about these remainders? Well, there's something that's called the remainder theorem, and it says when a polynomial is divided by a factor, x minus c or x plus c, the remainder is the same as if you were to evaluate the function at that remainder only. So here's a summary of what we've said so far. When a polynomial f of x is divided by a factor, we can find the remainder in the following three ways. We could use long division, we could use synthetic division, or we could just evaluate it at that value. So why are remainders important? Well, if we get a remainder of 0, then we know that x equals c is a solution, or what we call a root of the equation of the function. We also know that c, it's called a zero of the function. These are other terms you should know. A solution, a root, or a zero, they all mean the same thing. C is also an x-intercept of the graph. That's where it crosses the x-axis. And x minus c is a factor of the polynomial. So some important terminology there for you. The factors theorem says this. For a polynomial function, x equals c is a zero of the function if and only if x minus c is a factor of the function. So we would have to show that x minus c was a factor only by getting a zero remainder. So you can see the factor theorem and the remainder theorem are closely tied together. Here's an example. It says if f of 3 is equal to 0, write 4 equivalent statements that must be true. Well, based on our last slide, x equal 3 is a solution of the function. We could also say that 3 is a zero of the function. We could say that 3 is an x-intercept. And we could also say x minus 3 is a factor of the function. So those are all equivalent statements if we know that we get a zero remainder when we plug in the value 3. This example says to completely factor this polynomial equation using the graph that's given and also synthetic division. Well, synthetic division, if you look at the graph, it looks like we have a 0 occurring at x equals 1 and also at x equals negative 2. So I just went ahead and started with x equals 1 and then rewriting just your coefficients, and these are in descending order and we're not missing any terms, so we don't need any zero placeholders. So we're going to go ahead and use synthetic division, bring down your 3 to start, and then we multiply. 3 times 1 is 3, and then we add to get 7. And then we multiply 7 times 1 to get 7, and then we add and we get 2. 2 times 1 is 2, and we add to get a 0 remainder. So this shows us that x equals 1 is a solution. It is an x-intercept. So the factor x minus 1 is actually a factor of the polynomial. So when you write what remains, remember you're just rewriting the 3, 7, and the 2, and the power is 1 less than what you started with. We started with a cubic power, so this will be 3x squared plus 7x plus 2. So remember, these numbers are the coefficients, and then just add your variables back in. Well, this thing is not factored completely. We need one more step. So I went ahead and wrote, it looks like x equals negative 2 is another intercept. So if we put that on the shelf to the left and do synthetic division on what remains, we have 3, 7, and 2 are our coefficients. and then we start by multiplying. When we multiply, we get -6. When we add, we get 1. Multiply, we get -2. Add, we get 0. So now we can say x minus 1 was one factor. This one will become x plus 2, and this will be 3x plus 1, and it is completely factored. The rational zeros theorem says if you have a polynomial function with integer coefficients, then we can find all the possible rational zeros by looking only at the constant term and the leading coefficient. Now remember, these are not all solutions or zeros, but they're just the possibilities. So it will help you eliminate what the possibilities are. So if we have a function like this, we want to find all the possible rational zeros. So to find the possible rational zeros, we're going to find, first of all, p is an integer factor of the constant term. The constant term, when we're talking about the constant term, remember the constant term is this one right here. Okay, so those are all the p's. P's are the constant term. And then the q's are from the leading coefficient. So that's from the 6 right there. So let's go ahead and take a look. So find all possible rational zeros. Well, it's the quotient of those values. So what are the possible p-values? We're only looking at our constant term of 5. So the p-values are going to be plus and minus 1 and plus and minus 5. Those are the only factors of 5. The q values will come from 6, so we'll get plus and minus 1, plus and minus 2, plus and minus 3, and plus and minus 6. But to be a solution, it has to be the ratio of those two. So we're going to have 1 over 1, 1 over 2, 1 over 3, 1 over 6, all of those values. And then 5 over 1, 5 over 2, 5 over 3, 5 over 6. And it's positive or negative values. So of all the possibilities in the whole wide world, these are the only possible solutions to this function. So we've eliminated all the other numbers, and all of our solutions have to be from this list. So we can graph the function and find out which of the values are rational zeros. I've done a little graph here, and it looks like 1, 2, 3, 4, 5 is probably one of our rational zeros. The other ones look like they're fractions in here. So I went ahead and put 5 on the shelf, and then we can use synthetic division. Multiplying we get 30, adding we get 1, multiplying we get 5, adding we get -1, multiplying we get -5, and adding we get 0. So 5 is a rational zero, and that is in our list. Positive 5 is one of our options. So then we can go ahead and write our factors, x minus 5, and write what's left, 6x squared plus x minus 1. And then you could try some more possibilities to find, using synthetic division, to find the other two. Or if you remember how to factor this trinomial, it actually factors as 3x minus 1 and 2x plus 1. And so then this one would give us -1/2, which is one of our possibilities. This one would give us +1/3, which is also one of our possibilities. So that is completely factored using synthetic division and our graph. That's it for this video. See you next time.